Hello, welcome to the course SJPHY1C01 Properties of Matter and Thermodynamics. The contents of today's lecture is taken from Properties of Matter by J.C. Ubadhyaya. We will continue to discuss topics from Module 2, Surface Tension and Viscosity. In today's class, we are going to discuss about viscosity. It's a measure of a fluid's resistance to flow. In other words, it describes the internal friction of a moving fluid. Fluids with high viscosity resist motion as its molecular makeup gives rise to a lot of internal friction. So I can illustrate with the example of water versus oil seeping through a hole. So you will notice that water is going to flow freely, whereas oil flow is not as free. This is because oil has a higher viscosity compared to water, because viscous force is something which resists free flow. If you take another liquid known as glycerin, you will find that the flow is much more restricted, because if you look at this table, the viscosity of water is 0.8 into 10 to the power minus 3 Pascal second, whereas the viscosity of glycerin is much higher. Okay, so that's why compared to the free flow of water, the flow of glycerin is much more difficult. Viscosity is also related to the informal concept of thickness of a fluid. So if you take a beaker containing water and a beaker containing syrup, now if you put a spoon inside and rotate in water, you can see that you are able to move the spoon freely. On the other hand, in the case of syrup, you are not able to move the spoon freely, because compared to water, syrup is much more thicker, right? Here, thickness refers to viscosity. Syrup is thicker because syrup has higher viscosity compared to water. Viscosity plays a major role in determining the flow of a fluid. So basically there are two types of liquid flow. One is known as streamline flow or laminar flow. The second one is turbulent. Streamline flow is the slow, steady, smooth flow of liquid, which usually happens at a slower speed. And here, as you can see in this figure, liquids flow in parallel layers. Turbulent flow is just the opposite of streamline flow. Here, the flow is rough, irregular, and disturbed, and typically the flow speed is very high. It flows very fast compared to streamline flow. Now consider the streamline flow of a liquid over a fixed horizontal surface. So here the thick line is the fixed horizontal surface, which is at rest. So as I said, flow can be considered as flow of different parallel layers. All the particles in a particular layer have the same velocity. But if you consider different layers, the velocities are different. Typically, the layer which is in direct contact with the fixed surface remains stationary. This is because there is very high adhesive force between the liquid molecules and the surface, and because of that, the layer which is in direct contact with the fixed surface, this is stationary. When you look at the velocities of the subsequent layers, you can see that the velocities are changing. Typically, when the distance from the fixed surface increases, the velocity is also going to increase. So here, this arrow mark is a measure, the position of the arrow mark is a measure of the velocity. You can see as you move away from the fixed surface, the position is increasing, which means the velocity is also going to increase. Now, if you consider liquid flowing through a tube, so you know that tube is a three-dimensional object. This is a cylinder. So in the case of a cylindrical tube, each layer is going to be a cylindrical shell. So we are talking about coaxial cylindrical shells. So as I said, when you move away from the fixed surface, the velocity is going to increase. So when you take the two-dimensional view of a tube, you can see you have two fixed surfaces, the bottom surface and the top surface. As you move away from the surface, the velocity is going to increase, indicated by the position of the arrow mark, and expectedly the velocity is the highest at the axis of the tube, because this is at the farthest point from these two surfaces. Now if you look at the positions of all these arrow mark, you can see this corresponds to a parabola. In other words, the velocity profile of the streamline flow is a parabola. Now consider the motion of two adjacent layers A and B, which are at distances x and x plus dx from a fixed surface PQ, and the velocity of layer A is v, velocity of layer B is v plus dv. Now from this diagram you can note that for any given layer, the layer immediately below it has a lower velocity, and because of the cohesive forces between these two layers, the lower layer is going to reduce the velocity of the given layer. In other words, the lower layer is going to retard the given layer. On the other hand, if you look at the layer immediately above it, so this is at a higher velocity compared to the given layer. So because of the cohesive forces between these two layers, the velocity of the given layer is going to increase. In other words, the layer immediately above a given layer tries to accelerate a given layer. So you have two types of forces here. The layer below the given layer, it exerts a tangential force which tries to retard it, and the layer above it, it applies a tangential force which tries to accelerate it. And the net effect is a combination of these two. So the combinational effect is that the layer is going to experience a net tangential force which opposes the motion of the given layer. In other words, a layer is going to experience a frictional force that resists or that opposes the relative motion between the layers. So all the liquid layers are going to face this resistive force or frictional force. Therefore, in order to maintain relative motion between layers, or in order to create a flow, an external force must be applied in order to overcome this backward force. Typically, the external force is applied in the form of gravity or pressure difference. For example, if you take a tube filled with water, keep it perfectly horizontal, then there is no flow of water. But if you tilt it to one side, you will find that the water is flowing. This is because of the gravitational pull. So here gravitational pull acts as the external force which overcomes the frictional force between the liquid layers, thereby creating a flow. Similarly, you can create a pressure difference using a mechanical motor, an electrical motor, or a mechanical wheel. So here also the force associated with the pressure acts against the frictional force, thereby creating a flow. Okay. So in the absence of any such external force, the relative motion between the layers are destroyed and the flow stops. Now using this understanding, I can give another definition to viscosity. Viscosity is a property by virtue of which a liquid opposes the relative motion between its different layers. And the tangential force that tends to destroy the relative motion is known as viscous force. According to Newton, this tangential viscous force is proportional to the area A of the layer and velocity gradient dv by dx. I can write viscous force F is proportional to A multiplied by dV by dx. Since I am talking about a resistive force which is against the flow, I will add a negative sign here. I can replace the proportionality with a constant eta and write F is equal to minus eta A dV by dx, where this constant eta is known as coefficient of viscosity. Now, how do you define the coefficient of viscosity? Remember, for a liquid flow to happen, you need to overcome this resistive force by virtue of an external force, right? So if your resistive force is negative, then your external force is going to be positive, right? So imagine the external force required to maintain the velocity gradient dV is F is equal to eta A dV by dx. So the difference is that in the case of viscous force, you have a negative sign because it's a resistive force, whereas external force is in the direction of the flow, so you have a positive sign here. Now here, when you place A equal to 1 and dV by dx equal to 1, F is equal to eta. So using this, you can define coefficient of viscosity as the tangential force per unit area required to maintain a unit velocity gradient normal to the direction of flow. So if you look at this figure, you can find that the velocity gradient is always perpendicular to the direction of flow. Now, what are the units of coefficient of viscosity? From this equation, you can see that eta is nothing but force per area by dV by dx, or this is force per area into dx by dV. Now, unit of force is Newton, unit of area is meter square, and unit of dx by dV. Unit of length is meter, unit of velocity is meter per second square. So you have Newton per meter square multiplied by second. So this is one of the units. Or Newton per meter square is pressure. The SI unit of pressure is Pascal. So this is Pascal second. Alternatively, you can convert Newton, the force Newton, in terms of mass and acceleration, because force F is equal to ma. So Newton is kilogram meter per second square. So when you substitute for Newton, you get kilogram per meter per second. So these are the three different SI units of coefficient of viscosity. In CGS system, the unit is poise, and 1 poise is 0.1 Pascal second. Now, one important parameter which distinguishes between streamline flow and turbulent flow is the critical velocity. Critical velocity Vc is defined as the maximum velocity of the fluid up to which the flow is streamline. So below Vc the flow is streamline, and above Vc it is turbulent. Critical velocity depends on three parameters: 1, coefficient of viscosity eta; 2, density of the fluid ρ; 3, radius of the tube r. Now you can derive an expression connecting these four parameters. So we are going to follow a method known as method of dimensions. So we don't know the exact relation between these parameters. So we start with a general relation: Vc proportional to eta to the power a, rho to the power b, and r to the power c, where a, b, c are constant, which we are going to find out the values. The proportionality I am going to replace with a constant k, where k is known as Reynolds number. This is a purely geometrical parameter. This doesn't have any particular units. It's typically 1000 for narrow tubes. Okay. So my starting equation is Vc equal to k eta to the power a rho to the power b r to the power c. Now I need to find the exact values of a, b, c. So I am going to take dimensions of all the parameters. So we have three important parameters. One is mass indicated by m, length indicated by L, and time indicated by T. So all the dimensions can be represented using these three parameters. So on the left hand side I have velocity, which is length by time. So length is L divided by time, which is T to the power minus 1. K is dimensionless, don't bother about that. And eta, you know the unit of eta is kilogram meter per second. So this is m, meter is L minus 1, and time is T minus 1, okay, to the power a. And density is mass by volume. Volume is length cube, so ml minus 3 to the power b. Radius is distance, which is L to the power c. Okay. So on the left hand side I have Lt to the power minus 1, which is equal to, so let's combine the terms. I have m to the power a, m to the power b, which is m to the power a plus b. I have L to the power minus a, L to the power minus 3b, L to the power c. So this is L to the power minus a minus 3b plus c. Then I have t to the power minus a. So this is the equation. Now I am going to compare the powers on either side. First let's compare the powers of m. On left hand side there is no m term, which means this is m to the power 0. M to the power 0 equal to 1, right? So on the left side the power is 0, on the right side the power is a plus b. So I can write a plus b equal to 0. This is the first equation. Second, compare the powers of L. On the left hand side I have 1, on the right hand side I have minus a minus 3b plus c. This is the second equation. And third equation, minus a equal to minus 1, which is the powers of E. I have three equations, three unknown. I can solve it straightforward. So from the third equation I can write minus a equal to minus 1, from which I know a equal to 1. Simply multiply with minus 1, right? So you get the first constant a equal to 1. Now substitute this in the first equation. So 1 plus b equal to 0, and I know value of b equal to minus 1. Once you know the values of a and b, substitute it in the second equation, you will find that the value of c equal to minus 1. So you know the values of a, b, c. Substitute in the first equation. So Vc equal to k into eta to the power 1 rho to the power minus 1 r to the power minus 1. So Vc equal to k eta by rho r. So this is how you find the relation using the method of dimensions. So as I said, if the velocity of the fluid is less than the critical velocity, then it's going to be a streamline flow. If the velocity is greater than critical velocity, it's going to be a turbulent flow. Now you can see in the case of narrow tube, r is very small, r is in the denominator. So when r is small, Vc is going to be higher. Low density. Density is also in the denominator. So in the case of low density, Vc is going to be high. And high viscosity. Viscosity is in the numerator. So when viscosity is high, the value of critical velocity is going to be high. So in these three cases, the value of Vc is going to be very, very high, which means when you consider a liquid flow, the velocity of the flow is going to be less than the velocity of the critical velocity. So in the case of narrow tube, low density, high viscosity, typically the velocity of the flow is less than the critical velocity. In other words, the flow is going to be streamlined. On the other hand, if you consider a wide tube where R is very high, high density, rho is very high, and low viscosity, eta is very small, in this case, the value of critical velocity is going to be very, very small. So in such cases, the velocity of the liquid flow is going to be greater than the critical velocity and the flow is going to be turbulent. Now, as I said earlier, if you consider a streamline flow in a tube, the velocity profile is going to be parabolic. So let's derive an exact equation for this velocity profile. And we also want to find out what is the amount of fluid flowing per unit time. So this is an important equation in fluid dynamics known as Poiseuille's equation. So consider a liquid flowing through a capillary tube of length L and radius R by applying a constant pressure difference P between its ends. So there are three important assumptions. First one, the liquid flow is streamlined and is parallel to the axis of the tube. So all the layers of the liquid are parallel to each other. Second one, pressure over any given cross section is constant. In other words, there is no radial flow. Third one, velocity of the liquid layer in direct contact with the tube surface is 0 and velocity increases as we move towards the axis of the tube. Now let's consider a cylindrical layer. So the dotted lines represent a layer of the liquid. As I said earlier, a layer of the liquid in a tube is going to be a cylindrical shell. So this shell has two surfaces, an inner surface and outer surface. The inner surface is at a distance x from the axis. The outer surface is at a distance x plus dx. Let V be the velocity of the liquid inside the cylindrical shell and dV by dx be the velocity gradient. And we know the expression for the retarding viscous force acting on this layer, F is equal to minus eta A dV by dx. A is the area of this cylindrical shell. So how do you calculate surface area of a cylinder? You take the circumference multiplied by length. Okay. So if the thickness of the cylindrical shell is very small, then you can neglect dx. So radius is going to be x, circumference is 2 pi x, multiply with the length L, you get the surface area. So area A is 2 pi xl. So F is equal to minus eta 2 pi xl dV by dx. Now for the flow to happen, you need to give an external force. Here you are maintaining a constant pressure difference P between the ends. So the force associated with the pressure creates the flow. And what is this driving force? Force is nothing but pressure multiplied by area. So in the case of this layer, the cylindrical layer, radius is x, so the cross-sectional area is pi x square. Multiplied with the pressure, you get the corresponding driving force. So driving force is P pi x square. In the case of steady flow, the velocity is constant, which means there is no acceleration of the fluid. So here the forward force is balanced by the backward retarding force. So forward force is P pi x square, which is equal to the retarding force minus eta into 2 pi xl dV by dx. Now cancel the common terms, rearrange the terms, you get dV equal to minus P by 2 eta Lx dx. Now integrate this, you get the velocity V equal to minus beta by 2 eta L. The integral of x is x square by 2. Since we are talking about indefinite integral, meaning you are not specifying the limits, so you have a constant of integration C here. We need to find the value of this constant. As I have said in the previous classes, the value of unknown constant during integration can be found out using appropriate initial conditions or boundary conditions. Since we are talking about equations with respect to dimensions, we need to use the boundary condition. And what's the boundary? Boundary is the wall of the tube, which is at a distance r from the axis, right? So when x equal to r, we know that the layer which is in direct contact with the tube wall is stationary. Its velocity is 0. So boundary condition is going to be at x equal to r, v equal to 0. So let's rewrite this equation at this boundary. So we know that velocity v equal to 0 and x equal to r. So equation becomes 0 equal to minus p by 2 eta L r square by 2 plus c. From this I can note the value of c equal to p by 2 eta L r square by 2. Now substitute for c in this equation. So v equal to minus beta by 2 eta L x square by 2 plus p by 2 eta L r square by 2. Or the velocity distribution v equal to p by 4 eta L r square minus x square. Now let's plot this function. So at the axis x is equal to 0. So velocity v is going to be p r square by 4 eta L. At the walls of the tube x is equal to r. So r square minus x square cancels. So v equal to 0. For all in between points, you can note that p is a constant, eta is a constant, L is a constant, and for a given layer r is a constant. So velocity is a function of x square. This is a quadratic equation which is a parabola. So when you plot the velocity profile, you get a parabola as we have discussed before. Now what about the amount of liquid flowing or the volume of liquid flowing per unit second? The volume of the liquid flowing per second through this cylindrical shell of radius x and thickness dx. This is going to be velocity multiplied by area, because velocity is length divided by time. Length into area is volume, so volume by time. This is amount of liquid flowing per second. So capital V is going to be velocity small v multiplied by 2 pi x dx. So you have to remember capital V is not simply the volume. This is volume per second, volume per unit time. We know the expression for velocity v, so substitute for that, you get capital V equal to p by 4 eta L r square minus x square into 2 pi x dx. So this is the volume per second through the cylindrical shell. So if you want to calculate the total volume of the liquid flowing through the tube per second, you need to integrate it. And the limits of the integral are from the axis 0 to the wall, which is at a distance r. So this is going to be integral 0 to r p by 4 eta L r square minus x square 2 pi x dx. So take all the constants outside. So pi beta by 2 eta L integral 0 to r x r square minus x cube. Integral of x is x square by 2. Integral of x cube is x to the power 4 divided by 4. Apply the limits. You get pi p by 2 eta L r to the power 4 by 2 minus r to the power by 4. So simplify this, you get volume of the liquid per second flowing through the tube, capital V equal to pi p r to the power 4 divided by 8 eta L. This is known as Poiseuille's equation. So typically the pressure P is given as h rho g, where rho is the density, g is the acceleration due to gravity, and h is the height difference in the liquid column. Now Poiseuille's equation, it has some limitation. You cannot apply it to all the conditions because this is valid only for streamline flow. So in the case of turbulent flow, you cannot apply this equation. And it doesn't hold good if the layer in direct contact with the tube walls is not at rest, which happens in some cases, Also, it is assumed that P is used only for overcoming the resistive force, and no part of P is spent in giving the kinetic energy. So these are some of the limitations of Poisson's equations. So that's for today. Thank you.